Here we go. Projectile motion. Team sheet number 4, take 2. A baseball player leads off a game with a home run. The ball skims the top of the fence, which is conveniently the same height as the batter's swing. If the ball leaves the bat at an angle of 30 degrees from the horizontal with a velocity of 40 meters per second, how far is the outfield wall from home plate? Okay, so we're dealing with, the classic parabolic trajectory. Now this distance here is how far the ball traveled, and that's going to be our dx. And that's also how far away the fence is from home plate. Right? This is the batter, and this is the fence. And this path here is the path the ball takes. Okay. I'm also going to draw a vector representing, which is inaccurate. This is more than 30 degrees. I'm struggling real hard right now. So let's call this 30 degrees. And we need to find our two components, our Vx and our Vy. We know it's hit with an initial velocity of 40 meters per second, 40 meters per second at this angle, but we need our Vx and our Vy. Alright, what do we get? We're given that initial velocity, but we need to find our components of it. Alright, so let's find that. SOHCAHTOA, right? Ka sine of 30 degrees. Let me back up. Theta is equal to the length of the opposite over the length of the hypotenuse. So sine of theta is equal to opposite 30 degrees is our Vy. Our hypotenuse is 40 meters a second. Multiplying by 40 to solve for Vy. 40. Also, I'll go ahead and we know our theta, right? Our theta is 30 degrees. Our sine of 30. So 40 times the sine 30 degrees equals Vy. Okay, calculator time. 40 times sine 30 20. Does that make sense? That does make sense. So 20 meters per second is Vy. So our Vy is 20 meters a second. Now we're going to do the same approach, but for Vx, but we're going to use cosine, right? So cosine of theta is equal to the adjacent over hypotenuse. CAH, cosine theta, adjacent over hypotenuse. Adjacent meaning next to. So our cosine of 30 is equal to our adjacent here is our Vx. Vx is next to our angle divided by 40 meters a second, again, which is our hypotenuse. Multiplied by 40. 40. Whoa. 40 cosine 30 Vx, 40 cosine 30 Vx is equal to 34.64 meters a second. Vx is 34.64 meters a second. Okay. Now we know the dx, we know the Vx. So we can find t. What's the question ask us for? Question asks us for, we don't know dx, so we don't need to find t. God, these problems take forever, huh? So, we're going to have to use the half time here. Our trusty dy formula. Actually, not our dy formula. This guy here. If we say our Vf or our V2, right, y, is 0, because we know at the halfway point, at the peak of this projectile's trajectory, right about here, when it reaches its maximum height, its vertical velocity is 0. So again, we'll know our vertical velocity final if we're looking at only half of the trip as 0. We know our initial vertical velocity, we just found that using trig. We know gravity is always a constant acceleration, negative 9.8 meters per second squared, and then we can solve for t. So that's Vf, I'm using f instead of 2. Our final y velocity, again, this is considering only half of the trip, only from here to its peak, not the second half. Vyf, Vfy, our final y velocity, equals our initial y velocity plus at or gt, same thing. So this is going to be 0 meters per second. It's a beautiful M I just made. Equals our original y velocity was 20 meters a second. 20 meters per second plus negative 9.8 meters per second squared times our time. And so essentially what we're solving for here is how long does it take our y velocity to slow down to 0. Alright, so if we subtract this 20 here, negative 20 equals negative 9.8 t. We're going to divide by 9.8, negative 9.8, negative 20 divided by negative 9.8 equals t, equals going to be about 2. Negative 20 divided by negative 9.8, 2.04. That's the half time, right? The time it took for the first half of this trajectory, right? To slow down from its initial y velocity of 20 meters a second to the point where it had a y velocity of 0 took just about 2 seconds. 2 seconds. Okay, so then we know that our half time is, I'll call that t half, is 2.04. So our t total, or t, let's call it t total, it's going to be, let's just say 4 seconds. And then we can use our trusty dx equals vx times t. Our dx is going to be equal to, what was our vx? Let's go up and check. Our vx was 34.64 meters per second. 34.64 meters per second times our time was 4 seconds. dx is 34.64 meters per second times 4 seconds. It's going to be about 120, 138.56. 138.56. It's meters divided by seconds times seconds. The seconds cancel out. We get meters, which makes sense. That's what we're looking for. How far away was the outfield wall? 138.56 meters. That's how far this ball traveled in this entire trajectory. And assuming that it just got over the fence, that's how far away the fence is from home plate where the batter is standing. Now to take you through that real quick, we were given this initial velocity vector. We broke that into its components. It's x velocity and its y velocity. It's initial x velocity, its initial y velocity, using trig here. Now, once we found that y velocity, we used this equation here to figure out how long it took for this ball to slow its vertical velocity from its initial of 20 meters a second to 0, because we know at the peak its y velocity is 0. We found out it took 2.04 seconds for the first half of the trajectory to slow to 0. We doubled that because projectile trajectories are symmetrical to get our full time of 4 seconds, and then we used our x velocity times that full time, and we got the distance traveled in the x direction, which is how far away the fence is from the batter, which again came out to 138.56 meters.